Let us now focus on the response of the dynamic system for when the forcing frequency, capital omega, equals the natural frequency, omega n. G1 and G2, given by equation 10 in video 9, now become G1 equal to P0 over K times by minus 2 zeta over 2 zeta squared, which is equal then to P0 over K times by 1 over 2 zeta, which, using our definition for U static, is equal to minus U static over 2 zeta. G2 then becomes 0. The total response, which is equation 12 in video 9, then becomes ut equal to a cosine omega dt plus b sine omega dt times by the exponential function of minus zeta omega nt minus u static over 2 zeta times by cosine omega nt and the velocity, by differentiating this, then becomes minus a omega d sine omega dt plus b times by omega d cosine omega dt times by the exponential function of minus zeta omega n t minus zeta times by omega n times by a cosine omega dt plus b sine omega dt times by the exponential function minus zeta omega n t plus u static omega n over 2 zeta times by sine omega nt. For the steady state, we have u0 and u dot naught equal to 0. So, given u0 being set equal to 0, we can then say that a minus u static over 2 zeta is equal to 0. So then that a is equal to u static over 2 zeta. For the velocity at the steady state, we have b omega d minus a zeta omega n. That's equal to 0. That then implies that b omega d minus zeta omega n times by u static over 2 zeta, just by substituting in a, is also equal to 0. So for B, we can then say it is equal to zeta omega n times by u static over the damped natural frequency times by 2 zeta. If we note that as before, our damped natural frequency is equal to the natural frequency times by 1 minus the damping ratio squared, then we can say that B is equal to zeta omega n u static divided by 2 times omega n times 1 minus zeta squared, or u static over 2 times by 1 minus zeta squared. The response then, by substituting in for A and B, now becomes u static over 2 zeta times by cosine omega dt plus u static over 2 times 1 minus zeta squared times by sine omega dt times by the exponential function of minus zeta omega nt minus u static over 2 zeta times by cosine omega nt. Or, if we simplify this again, we have u static divided by 2 zeta times by cosine omega dt plus zeta over 1 minus zeta squared times by sine omega dt times by the exponential function of minus zeta omega nt minus cosine omega nt. A typical response then, if we plot equation 8, is given by the following: u over u static plotted against t over tn. We then end up with an oscillating function that is gradually getting larger and larger, and in a separate analysis we can plot a function that is always tangential to the peaks of this response. The magnitude of this envelope function we define as being u0, whereas this is ut, or equation 8. We do note, though, that the difference between the size of each successive peak in the response gradually lowers due to the effect of damping. Eventually it will settle on a maximum value that we've set here called u0, which is equal to u static over 2 zeta. For lightly damped systems, the sign term in equation 8 is small, and the damped natural frequency equals the natural frequency of the structure. So equation 8 now becomes ut approximately equal to u static over 2 zeta times by the exponential function of minus zeta omega nt minus 1 times by cosine omega nt times by cosine omega nt. This term that I'm outlining here with the dashed line is what we call the envelope function, which is shown here on this graph with the dotted line. We can use equation 9 to determine the number of cycles a structure needs to undergo prior to obtaining a steady state. If we define uj to be the peak value of displacement, after j cycles, then we can relate the number of cycles, j, to uj by setting the time, or defining the time, t, as being equal to j times by the natural period, tn, where, as we defined before, the natural period is equal to 2 pi divided by the natural frequency. In order to obtain the maximum amplitude in equation 9, we set cosine omega nt equal to 1. So, writing down again equation 9, which is u static over 2 zeta times by the exponential function of minus zeta omega nt minus 1 times by cosine omega nt times by cosine omega nt. Then with these assumptions, we can then modify this equation. So u, where t is now equal to j tn, is equal to u static over 2 zeta times by the exponential function minus zeta omega n, but instead of t we have j tn minus 1, and this is all times by 1 because this is now equal to 1, and this is also times by 1 because this is also equal to 1. We can now say then this is equal to u0 times by the exponential function of minus theta omega n j two pi minus 1 If we then divide uj by u0, because remember, when t is equal to jtn, this is actually defined as uj. We then have, in absolute terms, the exponential function minus theta times by j 2 pi minus 1, which is then equal to 1 minus the exponential function minus 2 pi theta j. This can then be plotted to get the number of cycles as shown in your lecture notes.